Thank you for the introduction. So I wanted just to go through some basics, nothing very complicated, for convex optimization. So I keep it quite simple, but I'll fill in proofs of all the statements, or pretty much all the statements I'm stating. So there will be a bit of scribbling with the iPad. So I'm trying to write very cleanly, but it's not so easy with the iPad pencil. So if there's any kind of issue of not figuring out what I'm saying, definitely ask a question in the chat. So I'll start off here. Very simple. Define what a convex set is, convex functions. I guess up to here, possibly most people know what that is. And then I'll introduce something that is quite important in optimizations. This is strongly convex functions. It's just an extra condition on convex functions. So I'll explain that. Afterwards, I look into minimization problems. So optimization obviously is usually concerned with either maximization or minimization of certain functions. So I'll discuss the minimization problem here, or one minimization problem. There's obviously various minimization problems in convex optimization, and state optimality conditions of a solution. So how you can test, for instance, if a solution is optimal or not. Then afterwards, I'll discuss how you can test if a method is the best possible method, or how you can measure the performance of a method, for instance, of the gradient method. In that context, I'll discuss the so-called Blackbox model, which is used to specify exactly what a problem is, what kind of information is available to an algorithm, and then you can analyze the performance of an algorithm compared to other algorithms. Then in a simple example, I'll state the rate of convergence of the gradient method and say something about optimality. Gradient method is actually in this context not optimal, but I'll say something how you can verify that. Here I won't go into details, but just give some pointers. If I'm be fast with the lectures, I'll have a final few slides on the Bandit problem and links to convex optimization. So the Bandit problem is a very popular problem for the last 15 years. It's a kind of simple reinforcement learning problem where you don't have a state, but various things are very similar to reinforcement learning. And there's a particular focus in the Bandit problem on exploration, how to explore efficiently while not losing too much payoff. So this actually often also used as a kind of meta reinforcement learning algorithm to do exploration in reinforcement learning. So I will not stay too much here, just state the problem and just give some pointers for how you can approach certain forms of the Bandit problem using convex optimization. So there's quite some links here. So that's kind of the conclusion, if I have a bit of time, of the talk. So I pretty much base the talk on two sources. The first one is really here's the main source for this talk. So if you're interested in reading up on convex optimizations, this one here is a book you should look at. It's from 2018. Nesterov is one of the big names in convex optimization. So this is a big 400, 500 page book, which contains what I'm saying today and much more. So if you're interested in convex optimization, I can just recommend this book here. Definitely a very good one. If you're interested in Bandit algorithms, this is a book you should go for. I think I've added a T too many, so it should be 2 T's for Lattimore. The book is also freely available online as a PDF, so you could just enter Bandit algorithms Lattimore with 2 T's instead of 3 T's, and the book should pop up. So this is a very good one if you're interested in Bandit algorithms, also pretty big and contains a lot of material. So I'll really just skim a bit through that with like 3-4 slides explaining some things. Okay, so for the outline. So I wanted to start with really slowly with what is a convex set first, before we go to convex functions. I often write here if with a double F. What this means is if and only if, so that two sides are exactly equal. If Q is convex, then the condition underneath holds. So if Q is convex, then this condition holds, and vice versa if the condition holds. then Q is convex. So the condition I'm stating here is for any 2 points in Q and any scalar in the 0, 1 interval, if you take here a convex combination of x and y, convex combination means lambda x plus 1 minus lambda y, since this needs to lie again in your set Q. So you can, if you like, visualize that. Say we take a circle, okay, not really a circle. We take 2 points in it. What this is saying is that the line between these 2 points has to lie in the set. So this here would be Q. So this would be a convex set. Alternatively, you can think of other sets, like say this one here. If you take 2 points here, you take a line between these 2 points, then the line wanders outside of the set. So here it will leave the set. So this set here is not convex. So Q is convex, this guy here is not. It's a very easy concept. Just every line between 2 points must remain inside the convex set. And this must hold for every points, for all points in the set. Okay, moving on. Next concept is convex functions. I've written here 2 definitions down. Let's start with the left side. So we have here Q, which is convex set. It's a pointer. Q is a convex set. The function f is called convex if, again, for all x, y in the convex set and all scalars in the 0, 1 interval, we have that f applied to the convex combination of x and y is upper bounded by the convex combination of the values of fx and fy. So what this is saying is, if you draw a picture, say we have f here, that would be the function. If we take 2 points, x and y, then the line above, the line that connects these 2 points must lie above the values of the function f. So for instance, if we take a point somewhere here in the middle, then the convex combination of this line must be above the corresponding function value here. So that is, I would say, the most common definition of convex functions. This again has to hold for all x, y in the convex set and for all scalars. So essentially any possible line between points has to stay above the graph of the function. This here doesn't make any other assumptions than f doesn't have to have any nice properties like being continuous or differentiable or anything. So you could, for instance, also have something that's not differentiable. You could have something like this, which is not differentiable because you have here a point which is obviously not differentiable. This function would also be convex. You can take 2 points. Any line between these would stay above the graph. Second definition that is often very useful is for functions f, which have certain nice properties. So these here are now for continuously differentiable functions. So this function here would be ruled out because it's not differentiable because of this point, but it would apply to this function. Here I changed from Q to RD. I think in the slides I move between Q and RD. RD itself is also convex set. 2 points in RD, if you take a line between them, will lie again in RD. So the second condition that we have is this one here now, is saying if I take a point fx, I take the gradient or derivative at x of f and go in direction y minus x, then I must stay below the point fy. So graphically, if I'm back in this curve, I take a point here, for instance, And I'm now taking the gradient in direction y, say y. First draw the gradient. So this would here be the line corresponding to the gradient, and I could have a y here, for instance. Then this point must be above the corresponding point that I get by moving in the direction of the gradient with y minus x. So that is the second condition. So essentially the linear approximation of the curve at x stays always below the graph of the function. So these are two very common conditions for convex functions. So what I wanted to say is left side here is the more general condition because you don't need anything particular. Right side here is specific because more specific because you need a continuously differentiable function. So this will not apply to as many functions as the left definition. However, whenever the right definition is applicable, then both definitions are equivalent. And I wanted to just show that, so I thought if I do here basics in convex analysis, it might actually be interesting to derive these things. They're not very difficult generally, just needs a bit of playing around with a few concepts, but I think these are quite useful to learn. So I was thinking I'll show just here the equivalence. So I'll try to, as I said, draw nicely. So let's say we define here a point x lambda. Is that too small or is that readable?
I think it's okay.
So this here would be the convex combination between 2 points x and y. So we now want to show that both definitions are equal when the function is continuously differentiable. So I will start with the going from the left to the right side. So I will assume the definition where the connecting line needs to stay above the graph, and want to show that this implies that the gradient will stay below the curve. Okay, so let's first start with lambda smaller equal 1. This here is just to rule out the limit case of lambda equal 1, which will make problems. So I have to take later on limits for the gradient, and I don't want to run into problems with the limit. So from the definition of convexity, we get directly that lambda f of x plus 1 minus lambda f of y is greater equal f of x lambda. So this is just the first definition that I've scribbled down on the page. So x lambda corresponds to the point above the graph and below the graph, and lambda fx plus 1 minus lambda fy corresponds to the line above the graph. So now you can just rearrange. This one here is giving you fy greater equal 1 over 1 minus lambda fx lambda minus lambda fx. And so this one here can also be rewritten as f of x. So sorry, I'm continuing on the left side, but I mean to extend the right end. So fx plus 1 over 1 minus lambda fx lambda minus f of x. So essentially what you're doing here is, just explaining that, what you're doing here is just observe that 1 minus lambda f of x minus f of y over 1 minus lambda is equal to minus lambda, 1 minus lambda f of x. And this one here, you can essentially open up the definition of x lambda. So this one here is equal to f of x plus, so opening up the x lambda, f of x plus 1 minus lambda y minus x, just rearranging here a bit with the lambda term of x, but that shouldn't be too difficult, and minus f of x divided by 1 minus lambda. Okay, so if you look now at this expression, this term here looks a lot like a derivative. So you have here this 1 minus lambda term. If lambda goes to 1, this term gets small. So you can think of this as an h. And the same term is here on the bottom. So this looks very much like a derivative. And if we take here the limit and let lambda go to 1, this actually turns into the derivative. So letting lambda go to 1, what we get is that fy, taking it from here, fy is greater equal fx plus nabla fx y minus x, which is the second condition. So that is going from the left side to the right side. So essentially you introduce the point on the line here, manipulate a bit the equations, but nothing really fancy going on. Essentially you start off with the first definition, rearrange, takes the limit, and you go to the second definition. I'm thinking, so I have until 45, is that true? How long do I have for the talk?
Yes.
Do I have like 11 minutes?
So just approximately, so the main idea is 45 minutes, but yeah, I mean, we started later, so you have still ample amount of time, and like, it's not very, very strict.
Okay, I think nevertheless, I think I'll skip the second proof. I mean, I kind of just want to highlight some techniques. So the second proof is the other direction is not very difficult, but I'll skip that and move on. I think otherwise I will run way over time. Okay, so all I really wanted to show here is both definitions are equal, this one and this one, if the function is continuously differentiable. The techniques to show these things are really basic calculus. Also the other direction, so there's nothing too fancy going on. So something that's definitely quite easy to understand, or let's say you don't really need deep mathematical skills to follow the derivations of these things. Okay, so moving on, I wanted to introduce strongly convex functions. This is an important class of convex functions that occurs quite often in optimization, also in the Bandit problem. So just going quickly here through the definition. We're working now again with continuously differentiable functions. F is called strongly convex if and only if there exists a parameter mu, which is called the convexity parameter. And then again, we have something that must hold for all x and y. What this is saying is fy is now greater equal the linear approximation that we have just seen. So we have here again the linear approximation, but now we have an extra quadratic term. So the function must also stay, the graph of the function must also stay above a quadratic increase. So it must bend more than, for instance, the functions that we have seen earlier. So this one here would not bend sufficient for strongly convex, would also not be continuously differentiable. So essentially what you want is a function, say it starts here, due to the quadratic term here, this function needs to increase with a certain magnitude at least. So anything that stays above it is okay, but it needs to have a certain quadratic increase. So the curve bends compared to this curvature here, essentially it's kind of flat or spiked. So strongly convex functions are particularly nice functions because of this property that they bend. I'm introducing down here some notations that I'll use later on. What this is saying is there's all these indices later on popping up. One refers to the number of times the function is differentiable here, and mu corresponds to the convexity parameter. So the convexity parameter essentially says how dominant the quadratic term is in the convex function. So higher convexity parameter means the curve has to bend significantly. Low convexity parameter and the linear approximation will dominate. Okay. Okay, so coming now to some optimization problems. I've written down here one basic optimization problem. You can really look at a million different problems here. But this is kind of the basic problem. We have a convex set Q, which is in this case a subset of Rd. We minimize a function over Q, so that is f here, and f lies, I think I've defined this earlier, but not said this. So this is a convex function, which is one-time continuously differentiable acting on Q. So we're looking for a minimum of a convex function, which is continuously differentiable over a convex set Q. So the first thing I wanted to point out here, so you might have seen, I imagine it when you read the book, the condition nabla f x equals 0 is necessary for a minimum. In this case, this is not true. You don't need to have nabla f x equals 0 at the minimum. Minimum I usually will denote here with x star. So it's kind of the solution you're looking for. And this condition is not necessary. So I guess you could now think for a second, why might this be? What is specific about the problem that renders this condition insufficient? And the answer for that is, if you think a second, I guess there's not too many quantities that can make problems. The answer is here, so set Q. So we have a constraint on the optimization problem. So the solution of the optimization problem might lie, if you like, in a boundary of a convex set. So if you say we have a convex set or something, it might lie here. But the gradient doesn't have, so this is Q, the gradient doesn't have to be 0 as it moves through the boundary. So the condition is not sufficient, sorry, not necessary for maximum or minimum. I think I have a simple example here. Yeah, so there's a simple example. I think that's useful. So we take a linear function, we take minimum x greater equals 0 just of x itself. So yeah, essentially the identity. And we look at the convex set Q, which is x in R, such that x is greater or equal 0. So we have a constraint. We are only interested in solutions for positive x values. So if you like, f of x here in the above notation is x. So the minimum here of this function is clearly x star equal 0. So that's the minimum of x, obviously. But if you look at the gradient, because this is the linear function or the identity here, so the gradient or derivative at x star actually everywhere is equal to 1, which is greater 0. So this condition here does not hold at x star. And the reason for this is the constraint set Q. The solution lies in the boundary. I guess you have possibly read in the book already this Lagrange multipliers, where you also have your side conditions. So this is in a certain way related. Okay, so what is then a good condition, necessary condition for optimum, for minimum or maximum? Here I've written down one. So we are again in the continuously differentiable functions. Q is convex. We also need that it's closed. So closed is a topological property. So for instance, the interval where you add the boundary point 0 and 1 is a closed set. The open interval where 0 and 1 are excluded would not be closed, just as some very simple examples. So the conditions we need here for this criterion, closed and convex set, and then a point x star is a solution to a minimization problem. Alternatively, for maximization, you could turn things around. If for all x in Q, so here we have to compare to all other points, it's not sufficient anymore to just look at the gradient at x star, but we have to compare to all other points. So if the gradient at x star evaluated in direction x minus x star is greater or equal 0. So for instance, in this problem here, the gradient in any direction x, which lies in Q, so these are all positive numbers. If I would look here into the inner product, x star is 0, so if I would look into the inner product, this would always be equal to x. I mean, the notation here is a bit overkill because we're on the real line, but this would always be equal to x and be equal, be always positive. So this is a simple example. The condition would be fulfilled. It would be always positive, whatever point x in Q would plug in here. So the condition would apply. Okay, so I think I have a proof for that, but I think we can skip that given the time constraints. So generally, again, this is not really too difficult. I think on my notebook, I have like 4 or 5 lines scribbled down on it. And obviously you can find the proof in the book. So if you care about that, have a look in the book. And I'll move on to some more topics. So generally, you're also interested in the existence and uniqueness of an optimum. So here I'm now looking at a further condition. So we are again in a simple setting, closed and convex set Q. Now here's a difference. Instead of looking at arbitrary convex functions, I'm now looking at strongly convex functions, at least one-time differentiable with convexity coefficient mu acting on Q. And then the statement here of this proposition is there exists a unique solution x star to the minimization problem. So you have an existence statement and also a uniqueness statement. Essentially, the uniqueness statement follows because the curve has to bend sufficiently. So you can't have a flat minimum where you kind of wander around and stay at the same value. Just looking if the... So I think the existence statement is a bit of work, so I don't want to do that, but I'm just having a look if the uniqueness, if I can just state this one here. Yeah, I think I can possibly just show the uniqueness. I don't think this is too much. So just showing the uniqueness part of the statement. So assume we have 2 minimizer, x1 star and x star, both minimize the function f. So we can write f star, by which I mean the minimum values that is attained, or if you like, f of x star. Sorry, let's use x1 star here. So we can now use the strong convexity. This one here, looking at essentially the gradients and the quadratic approximation starting at x star. So we just plug in the definitions that we had. So that was the strong convexity condition. So now, because x star is a minimizer, we know this thing here is greater equal 0, just by the condition we had. So this thing here is greater equal fx star plus we have x minus x star. So now what we can do is we can essentially, this here is equal to f star, can subtract f star on both sides. And what we get is 0 greater equal mu half x minus x star squared. So the norm, this is greater 0. So the norm between x and x star is 0, which means x is equal to, sorry for that. So x1 star is equal to x star, and both minimizers are the same. And we started here with arbitrary minimizers. So this is saying the minimizer is unique. There's a single point which minimizes. And really the intuition is you can't have a curve like that which stays flat. That would violate strong convexity. It has to bend, has to go up. There will be a unique point where the minimum is attained. Okay. Yeah, so these were now, just quickly summarizing what I've said until now, these were now different conditions for optima of convex functions over convex sets, or strongly convex functions over convex sets. Now I wanted to talk a bit more about the performance of methods. So generally, you're obviously interested in finding these optima numerically, and you're interested in how good a method like the gradient descent or gradient method performs, also how good it performs in comparison to other methods. So there's this general concept in optimization that people use. It's called this Blackbox concept. The idea is here to specify, I mean, the intuition is here to specify the problem exactly, to then be able to compare different methods on particular problem instances and depending on what information the models have. So here there's 3 lines in this box. The first one describes the optimization problem. So we minimize a function here of used RD, but you could obviously also consider convex set Q. So again, we're interested in minimizing a function f of x. We are looking at a particular class of functions. So this here looks a bit like bigger, yeah, a lot of indices, but essentially very similar to what we had earlier. These are strongly convex functions, infinitely often differentiable, and the first derivative is Lipschitz continuous. So I won't write down the definition of Lipschitz continuous, just saying it can't increase too much, and it has convexity coefficient mu. So we are here interested in this general optimization problem. So then a big question is, what kind of information has an algorithm available? So you need to specify that essentially to have a fair comparison between algorithms. If one algorithm only observes f of x, the value itself of a function, while another algorithm observes all higher derivatives, then obviously the second algorithm should perform better. The way how these things are quantified is through these so-called oracles here. I'm sorry, the pen stopped working again. Okay, I'll keep talking around this one. I don't think I need a pen here. So essentially the oracle describes what information the algorithm has available. So here is the so-called first order black box. I've scribbled down the different oracles below in these bullet point lists. So we have here zero order oracle, which returns the function value at fx itself. So any optimization algorithm which would make use of a zero order oracle could only use the function values in itself and no other information about the function. So the idea is here you describe exactly what the algorithm has access to. It only can access the function or the optimization problem through the oracle, and the zero order oracle would only return to the algorithm the function value itself. A first order oracle returns the function value f of x and the gradient. So for instance, the gradient method or gradient descent would be a first order method because it's based on the gradient and the function value itself. And then you have higher order oracles. For instance, the second order oracle would return fx, gradient, and the Hessian. Okay, so what I just wanted to finish with the approximate solution. So we have the model now, specified that. We have specified what information the algorithm has available. And now the question is, what are we interested in? What kind of solution? So here, for instance, it's written an approximate solution. So we're interested in a function x bar, a point x bar such that fx bar lies within epsilon of the best possible solution, and x bar as a point lies close to the solution x star. So both have epsilon differences. So you see a lot of these boxes, black boxes in optimization, specifying what your problem is, specifying the information, and specifying what kind of solution you're interested in. And that allows you then to evaluate and compare methods. So for instance, one method that I'm sure you're aware of is the gradient method, which is quite useful for large scale problems because it's cheap to compute. Just here, a quick recap. If you're in RD, idea is you take some initialization, x0 in RD, you iterate here over k, you compute fxk and nabla fxk. So essentially you ask the oracle, first order oracle, to provide you information at location xk about the function. And then you update by stating xk plus 1 is xk minus some step size here, hk. So there's various choices for that, obviously, times nabla fxk. So essentially what you're interested in when evaluating the methods, you try to understand how many calls to the oracle does a method need to solve the problem or find an approximate solution. So that's the performance measure here that you use to compare different algorithms. How many oracle calls do you need to solve the black box, so for instance, to find an approximate solution to your optimization problem. I think I can skip this one here. So I've scribbled down a proof for like deriving the rate of the gradient method. Possibly just might point out, obviously there's various results you can derive for strongly convex and convex functions relating various quantities bounding things. So for instance, if you look at equation 1, this is saying difference between fy and the linear approximation of fy, which is fx plus nabla fx. Y minus x is upper bounded by the difference between the points. And here a Lipschitz constant pops up, which, yeah, again, I won't go into. But there's various conditions you can derive for convex and strongly convex functions. So if you look into the book, you would find many pages full of these derivations. So yeah, I'll skip that. What I wanted to say here is you can now quite easily actually derive rates of convergence for the gradient method. because we are in the convex setting, or actually in this case here in the strongly convex setting, this is convergence to a unique optimum. So if you compare this to neural networks or other settings where you have many local optima, in the strongly convex setting, you have only a unique optimum. So here, these methods will actually find the optimal solution. And you can actually measure how many oracle calls it takes for the method to arrive at the solution. So let me just explain this slide here. So H here refers to the step size, if you like, to the learning rate. So that's here 2 over mu plus L. Mu was the convexity parameter. L is the Lipschitz constant. So this is here actually the optimal step size for the gradient method in the particular problem. Gradient method itself will generate a sequence of approximations of x star, here called xk. And you can now say something about how far xk is away from x star. So this is upper bounded by the original difference between the initialization x null and x star. And then you have this coefficient here, L minus mu, L plus mu. L is always larger than mu in these settings. And the important part here is the exponent of k. So the coefficient here in the big bracket is smaller 1. And as k increases, this thing will very fast get small. So this is called a linear rate of convergence. And essentially you have here really an exponential decrease in k of the approximation error. So xk will go rapidly towards x star. And then this then also translates directly into how good the function value is approximated. So the line below is saying fxk minus f star. fxk is always bigger than f star because f star is a minimizer. So we're interested in how close fxk is to f star. And here again, you have a quadratic, an exponential decrease in k of the approximation error and some extra coefficients like the L over 2 here. So these are very typical conditions that are obviously important for optimization, how fast do methods converge. And you can analyze these things in various contexts.
Stefan, my apologies for interrupting just real quick. If you need an annotation tool, I think Zoom also provides, so you can just write with it if that works for you. Just FYI.
Yeah, I think it's okay. I think if I would want to derive these things, I would, yeah, I think this would be not very practical with the whiteboard feature. Yeah, no, it's okay. So I think the high level is possibly sufficient. So really what you care, anyway, what I kind of want to communicate here is what are typical results that people in optimization look at. So what I've discussed earlier are these conditions for, you obviously have an optimization problem, and then these conditions for when a certain point is a minimum or maximum, when is the problem when does the problem have a unique solution, how can you quantify the performance as a method of a method, and yeah, how can you derive rates of convergence for a method. I also wanted to quickly say something about optimality of methods. So generally you're interested in finding for this particular black box setting the best possible method. So for instance, finding the best possible method that makes use of a first order oracle. The gradient method is actually not optimal, so it's a suboptimal method. So for that, I'll refer you to the book. It's actually not too difficult. You can actually compare here the rates that is derived on this page with the rates that other methods achieve. And there's other methods which also use only first order information, so only use a first order oracle, but achieve a faster rate of convergence. So you can quite easily verify if a method is suboptimal by finding another method that uses the same information, applied to the same problem, achieves faster, better approximation of your minimum. So there's another question you might ask, how can you check if a method is optimal? So generally how this works is people construct for particular model classes particularly difficult problems for which no algorithm can achieve a rate better than a certain quantity. And now if you figure out that your algorithm, like a gradient method or any other algorithm, achieves exactly the same performance as what this lower bound says, so the lower bound of what no method can go below or can be faster than. So if this upper and lower bound are matching, then you know that your method is optimal. So this is a very typical concept in various optimization and statistical or machine learning settings. So you have often upper bounds for some convergence, and you have lower bounds which say no method can converge faster than a certain rate. And if these two quantities match, then you know your method is optimal. And here in convex optimization, you can do exactly the same thing. So in the book, there's various problem descriptions which describe difficult problems where no algorithm can outperform a certain stated rate. Okay, so I'm not going into detail here. Is it okay for 5 more minutes?
Yes, please.
Sure.
Okay, so the last part, I just wanted to talk a bit about more of a machine learning problem, so closer to reinforcement learning. So just some outlook, because this is closely linked to convex analysis. So I want to talk here about sequential decision-making under uncertainty. So essentially a simplified reinforcement learning problem. So there's various bullet points here. The first one, I guess, would be more like a reinforcement learning problem. Obviously, everyone knows Go. Backgammon was very popular in the past, chess. How do you choose the next move? More common for the Bandit problems, the one I want to talk about, is the next one. So you might have multiple websites that you can show to a user. And you want to pick the one which is most appealing to the user. So how can you figure that one out from data and from past interactions with the user or with other users? Similarly, product recommendation. So you go to an Amazon webpage, which kind of products do you want to show on a webpage? It's again a kind of active problem where you need to make a decision, but it's a bit different from the full reinforcement learning problem in that you don't usually have a state space hanging around that you have to worry about. Traditionally, these kind of problems were considered in medical statistics. So for instance, drug design, which drugs should a patient receive? Or if you want to test if a drug is efficient, how to do these. So yeah, just some high-level figures. I guess you discussed reinforcement learning already. So the problem is very similar to that. You have somewhere a learner which interacts with an environment, so passes actions to environments, gets payoffs back or rewards back, and tries to use that to infer properties of the environment. Generally in these settings, like in reinforcement learning, you're interested in maximizing your reward over time. What's quite the interesting, the key problem in these kind of bandit problems is usually the exploitation trade-off. So typically in these settings, you're interested in making money as you learn from the environment. So it's not a kind of pure exploration setting where you can wander around in an environment and collect information without cost. But you also want to make money while learning from the environment. So exploration essentially then corresponds to collecting information from the environment. Exploitation refers to making profit from the knowledge that you have from the environment. And in this bandit problem, so multi-armed bandit framework, you usually try to balance these two. So in reinforcement learning, you very often care first only about exploration, understand the environment, and eventually find a solution. In the bandit problem, it's more common to look at this trade-off. So it's not for free to collect information. So for instance, say you're Amazon, You don't want to just present crappy suggestions to a user who will not buy anything for the next, whatever, 2 or 3 years, and afterwards you know what works for the user and you will present the right things. No, you want to also make profit while learning what works best for the user. So you somehow have to figure out ways to balance the information collection and making profit from the information. Okay, just another image. I'm not a big beer drinker, but I guess this is another exploitation problem, if you like. So you have multiple arms, multiple tabs here, multiple beers. So you can try one, can stick with this one if you like it, for instance. Might be beer you find appealing, or you could sample other beers and potentially find ones that you like more. So it's obviously in some way, again, a trade-off. If you explore more, you might also get a beer which doesn't taste well, which you don't like, or you might find a better one. And similarly here, you would have to balance exploring various tabs versus exploitation. And I guess you would have a fixed budget of how many beers you can try on an evening. Okay, so I just wanted to give a final slide here saying how these things link to convex optimization. So first off, I should say there exists a whole slew of bandit problems, depending on how the environment interacts with the user, which information is available to the user or the agent, how or when the reward is received. So there's millions. If you Google a bit for bandit problems, there are millions of different variations of the bandit problem. A particular popular one is the so-called adversarial bandit problem. The idea is here that the environment behaves adversarial to the user and tries to minimize the reward the agent receives. So it essentially would, I guess, on purpose give you a very badly tasting beer, or try at least to give you a very poor beer. And you as the algorithm or the user would try to still do well against this adversarial environment. And this problem has close links to convex optimization. So there's a popular algorithm. In this context, it's called the follow the regularized leader. And this algorithm is essentially based on strongly convex functions. It's related to what is called the mirror descent algorithms. It's an optimization algorithm, a very popular one, which is heavily depending on strongly convex functions. And you can interpret follow the regularized leader as exactly mirror descent in various contexts. So in these adversarial bandit problems, not only in this context, but more generally, you have strong links to optimization. Yeah, so just a bit of an outlook, and I think that was my last slide. Thank you.